can hide this. Okay. I can talk for another 60 minutes. I don't know how long this will take. I got over 100 slides. So I call it Rocky Mountain Memories. And I never went on a field trip with Ruth. And locally I did. I never went out west. I've never been on the ridiculous trips. But some of these places she probably did go to. Now, I'm not including visits that I did in my early childhood, like to Death Valley and the Mojave Desert for Barstow. Because I don't have any photographs, and it's a little bit off the Rocky Mountain theme. But I do have other memories in here, memories that go back to my college days, and then memories of the Rocky Mountains from personal vacations, which go back maybe 10 years. Two parts. The first part will be kind of mountain basics, kind of the fundamental geology, and I hope not to bore you. But this is the part I think Ruth would have liked just as well. You know, she took all the courses at GCP. So the objectives here, very brief. What are the Rocky Mountains? And then part two will be this photo tour of places that I've been to. And I'll try to relate where I've been to what we know about the Rocky Mountains and their formation. What exactly are they? So the two sets of tours are my college days, go back a little bit, and then some personal vacations that I've taken the past 5 years or so. If you have questions here in the room, I guess just let me know, raise your hand, and I can answer questions. There's another way you can ask questions, I guess, online, but I'm not sure.
They can use the chat function, or they can use the Q&A function. And online Zoomers, we can get to your questions at the end of
the talk, because you probably will have some. Now, this is a little, Rocky Mountains are kind of a new area of investigation for me. This is not local geology. I had to do some research on the subject matter. You know, maybe I should have learned it in my college days, but I didn't. But my personal vacations, I picked up a little bit more information about the mountains. But it's always good to go back and look at those pictures from your vacations and then study up a little bit. At least that's what I'd like to do. You know, these are great books like Roadside Geology of Colorado. Look at the whole set of the Rocky Mountains. Anyway, so the Rocky Mountains are part of the North American and South American range, Cordilleran range, or really it's a system of mountains. It's not one single range. But I'm going to limit this talk to simply North America. It gets more complicated if you go into Canada. It's the Northern Rockies, Canadian Rockies. You can even go into Central America. In fact, you could actually go all the way to South America, but that's far, far too complicated. Now, the extraordinary thing about the Rocky Mountains that we talk about here in North America is that if you get serious about this, you've got to specify, well, which Rocky Mountains are you talking about? Because there are actually two kinds of Rocky Mountains. There's the what we call the ancestral mountain, ancestral Rockies, and then the modern day Rockies. Now, the ancestral Rockies are long gone. They are associated with a mountain forming event we call an uplift about 300 million years ago. But the rocks that were involved in that uplift are actually 1.7 billion or older. I'll talk a little bit more about that later. Now, the modern day Rocky Mountains originated between, well, 55, maybe 85 million years ago. That was the period of formation of the modern day Rockies. And it's associated with a mountain forming event or orogeny called the Laramide. Then part two, we'll go into these memories where I describe like face-to-face contacts with these rocks and try to fit them into this, our understanding of the ancestral and modern day Rockies. So the Cordilleran, which runs from North America into South America, is highlighted in yellow here. It's one of the longest, perhaps it might even be the longest continuous mountain range in the world. These little shapes, these triangles, are the symbol we use in geology to illustrate what's called a thrust fault. That's where one block of earth slides up over another one. And there are lots of those thrust faults indicators in this map. In fact, the North American Rocky Mountains are probably characterized by this structural geologic process called thrust faulting. I'll talk a lot more about that later. Got to say a word about geologic time. I throw up, terms of million years around or a billion years around like they were nothing. And it's almost impossible, of course, to imagine the length of time that is a million years. Geologists can really only do that by drawing pictures and making diagrams. We use analogies too. No time for that today, however. But the point I want to make here is that we've got all of geologic time represented here in periods and eras and eons, and even smaller periods called epochs up there. But the ancestral Rockies got their start during a period of geologic time called Pennsylvania. It's about 300 million years ago. For comparison, the rocks here in the valley over just where I live in Turner's Falls, they're Jurassic age. Jurassic age rocks are about 200 million. So, but Pennsylvania rocks, which contain a lot of coal deposits in North America, are on the age of about 300 million. That's when the ancestral Rockies formed. Then, a couple 100 million years later, the modern day Rockies formed. Completely different mountainous ranges. But they are in roughly the same geographical location. They have different origins, but they are kind of in the same location. And so it could be somewhat easy to mix them up. As an aside, see the ancestral Rockies have long since disappeared. And it took about 245 million years for them to disappear and for the modern day Rockies to appear. We still see remnants of the ancestrals, but a couple 100 million years is what it takes to wear down a Himalayan scale mountain range to practically nothing. Another word about how mountains form. See, what we've got here is the continent of North America, and it consists of various parts. The inner part of the continents are called cratons or shields, but I use this word for craton. The Canadian shield is up here. The craton is rocky, platform rock. It's the erosion material from the shield, and it's the platform where their oceans are habitats are on the platforms. You see a lot of marine fossils on continental platforms. But now where oceans, where mountains form, is in something called an orogenic belt, and they're always kind of adjacent to the platform. This is almost universal. All mountains form in belts next to platforms. Except the Rocky Mountains. I'll talk about that in a minute. So now the rocks of the ancestral Rockies are, even though this uplift or this orogenic event occurred about 300 million years ago in Pennsylvania, the rocks themselves are hugely ancient, about 1.7 billion years old. That's my abbreviation, billion years, billion years old. And they're in the Precambrian period of time, geologic time, extremely old. There are remnants of these Precambrian rocks in Colorado, other states in the Rockies, such as Pikes Peak. But those are the age of the rocks in the mountains themselves. But the event actually occurs at 300 million years ago. And then over the next 500 million years after the next 500 million years after this 300 million year, no, I think after this Well, I'm going to skip that point to the next one. So now the ancestral Rocky Mountains contain, from what we can see today, remnants, really kind of the nub of the mountain, the Precambrian core of this mountain range in North America is expressed in Colorado at two basic mountain ranges, which have geologic names for them. We call them front rangia. Geologists use the term front rangia, or that associated with front range in Colorado, or the Uncompahgrea, which is further south. Do I have any? Looking for my clicker, my light. Do I have a? Yeah. The front range is up here. The Uncompahgrea is down here in the southern part of the state. Those are two ancient islands of the ancestral Rocky Mountains. Is pretty much all that's left of pure rock, and they do stick up. But these two mountains eroded down throughout the late Paleozoic to about the early Mesozoic era, which is 250 million years ago. Pretty much wore down flat, with the resulting sediment and cobble accumulating around the surrounding area. And that was and we'll see it was just lying in place during the time of the modern day Rocky Mountain Formation at about 50 million years ago. And we'll see the remnants of the ancestrals situated around the reformed modern day Rocky Mountains. Now, as I said, ordinarily the mountains form along the fringes, the boundaries of continents, never in the middle of a continent or of the craton. An exception, however, is for the ancestral Rockies, where during the Pennsylvania time, we saw some kind of event which uplifted those very, very ancient Precambrian rocks right up through the Paleozoic rocks that were being deposited at that time. And that was the formation of the ancestral Rockies. So what caused the ancestral Rockies to form 300 million years ago is still a question for debate. Very likely it was a collision of some tectonic plates. This is often the usual suspect when we see mountains forming. So was there a collision of continental plates 300 million years ago? Sure enough, there was. We see a collision here of Africa joined up with South America, colliding into, well, the ancient proto-North America, which we call Laurentia in geology history. And that collision is about here. This could probably was the factor that caused the uplift of the Precambrian rocks that formed the ancestral Rocky Mountains. Two more factors to consider. Well, so far, well, that's about as much as I'm going to say about the ancestral Rockies. We'll see the rocks themselves. Let's talk about the modern day Rockies. Two things we need to consider when we talk about the formation of the modern day Rockies. Well, the whole event begins about 55 million years ago, or maybe 80 million years ago, and continues about 50 million years ago. Two things we need to talk about are terrains, spelled that way, not that way. And then later on, it's the laramide or orogeny. These two factors are the important factors in the formation of modern day Rockies. Well, what the heck is a terrain? When I went to school in college and went to the GIU field school in Montana, we needed to talk about terrains. This is still a relatively new idea. What we're seeing with terrains is that there are like minor, small scale mini continents, maybe on the scale of Greenland, in the middle of oceans that get picked up on on oceanographic lithospheric plates and are carried toward continents, crash into the continents, and accumulate like dust in a dust bunny. Now we realize that continents are actually they're not formed only by volcanic activity, let's say, because of crashing plates, but because of what we call accretion of microcontinents that get stuck at the orogenic zones of cratons or continents and remain there because they cannot be subducted under the plate. They can only accumulate on the edges. So continents grow by this process called accretion, which is a result of these terrains being carried and added to the orogenic, added to the continents along the edges over periods of millions of years. That's terrains. They make continents bigger. They also make them more complicated to study. That's why this is a relatively new concept. Now, the laramide orogeny, or mountain forming event, was very peculiar. Starting about 80 million years ago, the ocean plates in the Pacific were beginning to be subducted under North America, but along comes the Farallon plate, which no longer exists, by the way, it's completely gone. The Farallon plate, however, was subducted at a very shallow angle. Why? We don't know. This is mainly a hypothesis, but it's the best one we've got. So the subduction of this Farallon plate at a very shallow angle goes under North America. And because it's a shallow angle, there's a lot of friction, slow moving, I suppose. There's friction. Thrust faults begin to develop, which means that there's pieces of crust that are sliding up over overriding plates, and they pile up. That's indicated by these lines here with the funny tooth marks. So the thrusting is coming in here, and then a little bit further east into North America at this time, you start to see these, what we call laramide uplifts. The laramide uplifts are really just thrust faults that push the crust up. Notice when I say thrust fault, I mean it's the upper plate is being pushed up over the lower plate. Think about what that means. That means older rock is actually being pushed up over younger rock, completely reversing the sequence that we would expect, with younger on top, old on the bottom. But if you've got a thrust fault, the old is down here, but that's thrust up on top of younger stuff. And that was going on all over this region here during the modern day formation of the modern day Rockies. Okay. So, yes, thrust faults. They're sort of like playing cards that you can spread out. They slide on each other. You can push them and slide up over the. Did I have a better? Yeah. I'm looking for a slightly better illustration. Here's one. This block, which you call hanging wall, is being pushed up over the lower block. What's characteristic about these thrust faults in the modern day Rockies is that there's usually a high angle of tilt here where the thrust block reaches the top of the stack. There's usually that angle, the rocks are tilted at a pretty high angle. And we'll see that in the remnants of the ancestral Rockies even today. This is a nice hand sketch. I showed it several times in my talk. Here we have the core rock of the Rocky Mountains, which is pre-Cambrian in age, meaning 1.7 or older billion years. It's the core. It was started, the uplift began about 70 million years ago for the modern day Rockies. It pushes up all the ancestral rocky mountain layers. Well, these are actually the remnants. These are sandstone sedimentary rock layers that have been pushed up at a rather high angle. A couple of the points on this hand diagram we'll be visiting, or I visited a couple years ago. The dinosaur tracks, the Dinosaur Ridge at Dinosaur National Monument, the Red Rocks Park Amphitheater in the suburbs of Denver. Maybe you've been there. It's fantastic natural amphitheater situated between these tilted rocks of the ancestral Rockies. But what we look for is steep angles at the flanks of the modern range, and that indicates that there's this thrusting going on. And this is the erosional remnants of the ancestral Rockies. We'll see examples of Dakota. I've got examples of Dakota. We'll actually see the rock, the Morrison Formation rock itself. That's the one that has all the incredible dinosaur bones. Okay. The Dakota hogback are those steeply tilted rocks. There's you see the Dakota Formation is right here. The Dakota group is steeply tilted, and tilted, sticking up. It's tilted to the southwest, but there's the rock as it is exposed in the photograph. You take a drive from Denver to where my brother lives in Frisco. You go right past this outcrop. I saw this on the drive back from the airport. I thought, what the heck is that? Well, that's the Dakota hogback. That's this Dakota group right here, tilted on edge, and we're driving back from Denver's to the well, actually, Frisco is to the west, Denver's to the east, so we go right by the Dakota. And the Dakota group is right there. I-70. The Denver Red Rock Amphitheater, see how tilted those are. The amphitheater itself is situated exactly right in the middle of two fantastic formations. They have hundreds of groups there every year. It's a very popular venue. Okay, just after this mountain forming event called Laramide, we end up with a pretty high plateau. Tibetan scale, 20,000 feet. That's pretty doggone high. And in the last 60 million years since that uplift event at the Laramide, erosion has stripped those high rocks, and you can see the ancestral rocks below, and everything's exposed there. If you know where to look, you can see the ancestral Rockies situated in there with the modern day Laramides. Covered a lot of geology in 5 minutes. Questions?
So, yeah, is the Himalayas, the Tibet plateau, is that basically as large as mountains get when you have the collision? Is it believed that there were any mountains that were larger in the past?
I don't know. There've been some pretty high ones. It all depends, I guess, on the strength of the plate collision, the intensity of the collision, which forces the uplift. So there's two factors. It's the rate of uplift of all of that rock. And then there's also the rate of erosion or the weathering of that rock as it rises. Now, the Himalayas are still rising. That was a result of essentially India crashing into Asia. The Alps are still rising as well. They're pretty high, not as high as the Himalayas. But so there's the erosion, the weathering factor. If weathering is faster than the uplift, you might actually see mountains begin to shrink, even though they are rising. But if the erosion and weathering of the mountain is not as fast as the uplift, then you see the mountain grow. I mean, if the erosion were at the same rate as the uplift, you wouldn't see any growth. So it's a combination of two factors. And I don't know if geologists have figured out which is the highest mountains in the world. But they all come up basically from sea level. Because there are fossils in the uppermost rocks of the Alps, marine fossils.
I want to see if anybody asked you questions in the chat.
We
Helen,
No, no, yet. I thought I said it back to the beginning, I didn't. No, we're pretty sure. Pretty sure. All right, I'm not able to follow up with that, so we'll have to check it at the end, so.
Check at the end. Yep. So now part two, let's hit the road and look at these spots that I've been to over the course of my career. And Rocky Mountains are situated right here. This is a simple Google map. I just, we have Google Earth and I put in on the search line, Rocky Mountains. The Rocky Mountains are right there. There is a Rocky Mountain National Park too, which I never visited. That's not included in my travels here, but the Rocky Mountains are in this area right here, of course. And the little tacks are places that I have been. We're going to be looking at all of these up here for sure, and a few that are down here. Because of the time considerations and whatnot, I'm not including Death Valley or Barstow. And actually, I've only been to the Grand Canyon as a 4-year-old. And it's not strictly a mountain, but it's an amazing valley. But I actually don't talk about it because that's another talk. But each tag there is going to be a memory that I'll talk about. So the first trek is my college field trip in the summer, last summer of the graduation as an undergraduate at Indiana University at Wilmington. You have to sign up for a field experience, a field school, a field class. There's a long one, which is 2 months. I took the 6-week one, but nevertheless, whether it's long or short, we hop into vans in Bloomington and we drive west. And maybe 7, 8, 9 vans, rather large group. Class is rather large. The IU Bloomington Field School is one of the best in the world. People from all over the world come to the IU Field School to go on this trip. Of course, if you're an Indiana resident, no problem, you get in automatically. But the competition, if you're, from Canada or if you're at an Ivy League school, it's pretty tough. So, a lot of Ivy Leaguers with us in this group. Anyway, we visited the Badlands National Park, Devil's Tower, Glacier National Park, Yellowstone, and then we end up at the field school in the Northern Rockies, which I call the Tobacco Leaf. I'll briefly talk about each one of these stops. Now we start our first stop is really at the Badlands in North South Dakota. Mount Rushmore's in there, but I don't talk about Mount Rushmore. Why do we start? Well, first of all, why do we go on this grand tour to begin with? This is always a main feature of any kind of geological education. And this would have been something that Ruth would have loved to death. You got to go out into the field. You got to go driving around at different spots, see these rocks in their natural setting, climb around, look at them from above, from below. That's what we do in field geology. But the first stop here is at the Badlands, and it's really not mountains. It's a valley. It's a receptacle for sediment. Valley topography, valley geology, it's not mountainous. Why would we want to start on a valley? Well, the key here is that the valley contains all the sediments that really provide the record for what has gone on in the mountainous areas previously. Those mountains are wearing down. Cobbles and gravels and stuff fall into the valley. They're turned into sand and silt. Eventually, you get formations, beautiful formations in the Badlands that look a little bit like this. I don't have a camera on that trip, so I just get things off the internet. So the Badlands are not that bad. They're very beautiful. They're loaded with interesting rocks. You can study the repeating processes of deposition and erosion. And notice that the deposition in the Badlands begins about 75 million years ago and ends about 28 million years ago. That pretty much brackets the laramide mountain forming event, period. 28 to 75. Another reason is that this is a place to find really incredible fossils. Dinosaur bones are there, many other kinds of fossils, many fish fossils are there from the Cretaceous. But that was covered with an ocean. My point is that these valleys, these rocks in a valley or in the Badlands so-called are very valuable because they are the records. They provide the documentation of the record of what has occurred in this region and in the rocks in the mountainous areas. The geologic map of the Badlands. There's the Badlands right there. And Rapid City, the Black Hills, the main formations in the Badlands is the Pierre Shale. It's very fine grained, marine, deep water, marine sediment, meaning the environment was a deep ocean. And that is right over here. We have a cross section of the boulder area, east to west. Pierre Shale is included. To the east, Denver is, I believe, somewhere central there.
You're in Wyoming, I think.
Oh, Denver's down here. That's right. But the formation runs across these states. So Denver's over here. The Pierre Shale is over here. Pierre Shale is huge formation. Then you have all these other formations. The Morrison is right here. That's the dinosaur formation. Here's the these are the formations of the hogbacks. This is the remnant of the ancestral Rocky Mountains. Pike Peak is in this block of metamorphic granitic rock. Anyway, we start our trip kind of at with the younger rocks. Pierre Shale is younger, and then we work to older rocks and we call that in geology going down section or going back into time. It's quite appropriate, therefore, to start with Pierre Shale because it's the most recent rock of the recent region. And we're heading. Next stop, Devil's Tower. Something more of a tourist attraction than a geologic site for us because we really didn't get out to study this rock. But we're on our way to Yellowstone. And we're at Devil's Tower, which is right up here. Rapid City's down here. One thing for sure that we can say about the Devil's Tower is that it's volcanic. Exactly what it is in terms of that volcanism, we can't say for sure. But for sure, we are inside something that is certainly volcanic. Formed about 50 million years ago, during the time of the Laramide erosion. And then between 5 and 10 million years ago, the whole thing began to erode away. The formation of the tower is speculated to be something like this. There are 4 theories as to what this tower is. And they're all volcanic. It could be a stock, which is kind of a big blob of lava, which resides underground and just cools. And the sedimentary rocks on top here can be eroded away. And actually this part of this stock can be eroded away. What's left is the tower structure. That's one theory. Could be something called a lapolith. That would be some kind of blob of lava embedded between layers of sedimentary rock. It didn't break through the sedimentary rock like the stock did, but it just cooled in place like a blister. Could be a combination of those two, actually. A volcanic plug? I always thought it was a volcanic plug myself. This particular tower, of course, is famous from the movie Close Encounters of the Third Kind. I haven't seen it in that yet. But it could be a volcanic plug, which means it's like the remnant of a volcano, and this is just the track. The lava was passing through this passageway through this tube on its way to the surface. Everything else has been eroded away. This is what all that's left. It's a plug of an ancient volcano. 80 million years ago. Then there's a new theory out there, I'm not familiar with this one at all, where this is a result of magma coming up into the crust, interacting with groundwater near the surface, and then turning into with this kind of structure. It's called a Mar diatreme. That's hard to explain, but it is one of the more, there's 4 different theories of where the Devil's Tower came from. Why is it called Devil's Tower? There's a giant causeway in Ireland, and these are very peculiar expressions of volcanic rock. It's called columnar basalt. And you can have columnar cooling in this very peculiar columnar pattern. We see it actually here at Mount Tom in our valley. Here are just spectacular versions of columnar basalt. And this is the Giant's Causeway. And that's kind of a devilish look. You just sort of wonder what could form that, but it's completely natural.
Wait, where's the causeway?
In Ireland.
This is in Ireland. Causeway.
Oh, where in that photo is the causeway she means?
What exactly is a causeway?
It's sort of like a
Is it a
road,
road?
like a road across,
Yeah.
separating 2 bodies of water.
I've never been there. I didn't know that there was a road associated with
So
it.
maybe it's
This
just,
is word causeway to me. I mean, there's a causeway that connects New Brunswick with Prince Edward Island,
Right.
9 miles.
maybe,
Well,
maybe
Yeah.
at low tide, it looks like a road. Maybe if you're looking at a photo at high tide.
there's going to be a salt surface, probably connecting that. That's a sea arch, actually, connecting that with the mainland. This looks like a walkway. It's a walkway for the devil. Yeah.
In this case, it's a passage with water. I think the problem is actually that.
Through here.
Yeah, that's my guess.
Okay, these are all good guesses, and I have to guess with you because I don't know. I have to go to Ireland. It's my next talk. Anyway, the reason it's so devilish, I think, is because of the phenomenal, this is 8-sided columns. It looks like it's just otherworldly. That's why we call the Devil's Tower the Devil's. Moving on to Yellowstone National Park, next stop after Devil's Tower. This happens to be one of the world's most fascinating of all national parks in the world. You might wonder why. I don't really, because there's everything in it. There's wildlife, there's volcanism, including all those geysers. You got lakes and waterfalls. You got canyons, the Little Grand Canyon of Yellowstone, glaciation, and then of course the geology, which actually causes all that stuff. It's incredibly interesting because the geology is fascinating. The main point about Yellowstone National Park geology is that the park sits on what's called a hotspot. The thing to remember about a hotspot is that it's a plume of the magma shooting up from probably the upper man. And the position of that plume, well, shoots through the crust, makes a hotspot, but the location position of that plume is quite stationary. It doesn't move over tens of millions of years, maybe hundreds. You'd think it would, but it doesn't. What does move, however, are the lithospheric plates. The plates are moving over the top of the hotspot and burning a hole, so to speak, in the crust, just above the plume itself. It's like a lava lamp. These plumes are like lava lamps. You got wax and oil. You heat the whole contraption down here, and then the wax begins to rise, which is less dense than oil, and you get a head, you get a kind of a neck. Believe it or not, this is the way geologists model these things, like lava lamps. So the plume stays stationary, the plate moves. So my water bottle is the hot spot, and this is the lithospheric plate. place moving like that, you'll get a pattern on your plate, burn pattern, which tracks the movement and rate of movement of the plate relative to the station. Now, when we look at the region out there, we look at the several states combined, Idaho, Oregon, Washington. Well, we see a lot of volcanic activity going on here. There are volcanoes, active volcanoes still today in this area, due to subducting plates. The hotspot, however, has remained stationary. Not to say that these have remained stationary, but the plate has moved in this direction. So we see the oldest evidence of hotspot volcanism down here. That's 16 million years ago. Here's 12 million years ago, 6.5 million years ago. 1.32 and 0.6 million years ago is pretty much the current location of where the hotspot is expressed in the North American atmospheric plate like that. So we use this kind of method to figure out speed and direction of the plate movement. We sample the magma coming up out of the volcanoes that are expressed here. You can also figure out maybe the origin of the magma itself. Might help us to explain why these hotspots are so stubbornly stationary over time, which is still a mystery. Next up is Glacier National Park. We're still in the vans, by the way. We're still driving around. So we're heading up to Glacier National Park. Not so much not a mountainous region, but again, an erosional area. This is where we see illustrated the erosive power of glacial ice, water to remove rock and to sculpt rock into Glacier National Park. Really, one of the most beautiful national parks in the country. There are two kinds of glaciers. Actually, both are up there, or what were up there. You have continental glaciers, which are on a scale of the entire continent. They occur because regional hemispheric climate plummets, temperatures drop, and there's more formation of ice than there is melting. Glaciers will form. You can also have alpine and mountain glaciers. We still have those today, although they're all shrinking. And they form in high elevation places where the air is thinner and the temperatures are cooler. Again, more ice can form there than melts in the summer, and you get alpine glaciers. Alpine glaciers all over the world are shrinking. We have continental glaciers, somewhat still in or ice caps in Greenland, but even those are shrinking. This is the retreat of the ice sheet to about 11,000 years ago. So the ice in the Glacier National Park region. The ice, when it retreats, pulls rock, literally will pluck rock out, carve out rock to make characteristically U-shaped valleys, which we see here. Beautiful picture of glacier. Gonna hike up a little bit to see that. Other pictures of glacier are over here, but characteristic U-shaped valley. The glacial ice would sit in this valley and move down slope. If it stays put for a while, it creates a little lake on its descent down the mountain. We call that a cirque. All of these features are visible in Glacier National Park. That's why we're there. But we had to go on. Next stop, which is really kind of home base for the next 6 weeks, is at the Indiana University Geology Field School in a minor range of the Northern Rockies, which are called the Tobacco range of the Northern.
Why is it called tobacco?
Well, we name things in geology after local names. There might be a town called Tobacco or Tobacco Root. You know, the Jurassic Turner's Falls Formation. Why do we call it Turner's Falls? Because we see it best expressed in Turner's Falls.
Well, also there's a waterfalls.
right, but the formation is named after Turner's Falls.
It's named after the village of Turner's Falls. We name rock formations after local place names. So there's some kind of local place name called tobacco. The field school is located right there. This is a little river, so kind of easy to get to. There's a road that's you can get in and out of the field school quite easily. There's the road itself. This is Google Maps or Google Earth. I just did a search for Indiana University Field School and I get this. What's really interesting to me as a student is this structure right here. There it is, unhighlighted. A band of rocks kind of bending itself around the field school. What is it? It's just simply folded rocks. You know, the rocks start out flat, and then they're folded like this, and then tipped up on edge, and this is cut off. You get that. Spend hours in the geology classes learning how to visualize this, this, this. And sometimes it's this, this, and this. Things are turned upside down. Well, we learn all of that at the field schools. So this is really an excellent place to learn about structures of rock, the beauty of the structures themselves, and the types of rock, and the history, which is all a result of the modern day Rockies, Northern Rockies, the Laramide, and Roger. Reviewing some recall that it's subducting plate, it's subducting at a shallow angle. The result is we get a lot of thrust faulting, rather far interior into the continent. And it makes for kind of a complicated thrust fault terrain that looks like that to a professional. Not to, the students, we were familiar with these kinds of drawings, but these are all thrusts. And there's thrust faults within thrust faults. There's a sequence. So if you start mapping these rocks out, it repeats itself, which can drive you crazy. So you're walking along, this road here, mapping your, trying to figure out what rock formation you're in, and you think you're going back in time or maybe forward in time, but actually it's like being in that movie Groundhog Day. You keep going back to the same rock. Why? Thrust fault. It'll drive you crazy. That's one good reason for sending students out. Not to torture them, but it's a good learning. This is another example of a thrust fault in Canada. You can sort of see, I can see anyway, the rock itself being pushed up. This is older rock and pushed up over. Perfect laboratory for geology students. One of the best schools in the world. Now we're going into personal vacations. Am I going on time? 11:56. Am I okay on time? Keep going. Keep going. Here we started in Las Vegas. We flying to Las Vegas this vacation. Drive to Bryce Canyon National Park. Next stop, Capitol Reef National Park. Maybe you've heard of these two national parks. I bet you've never heard of Ticket Wire Dinosaur Trackways. Then we go to Dinosaur Monument and another vacation, and then we end up at Denver and Red Rocks. The Bryce Canyon National Park is in southern Utah, down there with several others, by the way, but we had to pick and choose. We picked Bryce, and in a moment I'll show you Capitol Reef. Bryce is really just otherworldly. There's no place else in the world that looks quite like Bryce. It's fantastic. You've probably seen it, right? Maybe you've been there. You've been there? I haven't been there. It's just weird, utterly weird. They're called canoes. they're due to, entirely due to erosion, due to water, but then there's some frost action too that is occurring. So the rock is fractured, water gets into the fractures, forms ice, spans the crack, there's crack, expands the crack. Water comes back, enlarges the crack. But then towers are formed because presumably there's like some kind of weight which caps this column, this pinnacle, and sort of inhibits the erosion, keeps it in place. And these towers can be quite high. These are all my photographs, just hiking the trails around the valley, the canyon. You can actually hike down into these slot canyons too. If rain is predicted, they would prohibit you from going down there because you might get inundated. It's a pretty easy place to get around. Another panoramic view. With my finger in there. How do they form? I'm not going to go into detail except to say this. You start with basically, a river basin, just a watershed, typical kind of normal river stream relationship called a watershed. Then there's a fault. Faults are always at play here in the West. There's a fault, and that makes that kind of intensifies the erosion on the upside block, and it begins to erode away to produce these pinnacles of Bryce Canyon, which are the result of, I think I've got some, here's some more photographs. Differential erosion of the blocks themselves due to ice and water. And then there's this cap that sits on top of the rock, which kind of holds the whole thing in place. It's hard to believe that this actually forms, but there it is at Bryce. Next stop is Capitol Reef. It's quite close by. So we drove over to Capitol Reef. It's one of the least visited national parks in the country. It's kind of in an out of the way location, I suppose. It has spectacular rocks, but it's kind of famous something called a monocline. And it all depends on, there's a lot of history down here. The wagon train people had to break their way through these rocks, which they call reefs. That's what got the name Capitol Reef. The monocline forms what they call water pockets. This is not a geology term, but I was familiar with. But this water pocket is a fold, and it formed about 50 to 70 million years ago, which brackets the laramide orogeny, so you know that they're related in some way with the laramide orogeny. It looks like this, simplified. So you've got a fold, and rather than having a fold with two limbs like this, it's a fold with just one limb. And they call this, I believe they call this kind of pocket. You have a fault here. This rock goes down, this rock comes up, produces a fold in those rocks. And now these little pockets are places that, well, you can explore the pockets. You can, because they are very long, linearly long. And you're within the same formation, and you can look at beautiful rock cliffs on either side. So that's what we did. We would walk down these pockets.
Are these pockets oriented north-south or east-west, or?
It appears they're, in this case, north-south. They don't have a larger map of the park itself. That looks like the axis of the fold coming out as the north-south, west and east. Notice some of the formations here. You see them before Morrison Formation. We'll see that again when we go to Dinosaur National Park or National Monument. Dakota, this is the hogback formation. A lot of these are sandstones because this is the interior. Formerly, it was the interior of the continent, North American continent, before the Laramide, and this is all desert rock. Sandstones from desert environments. So utterly beautiful to walk in these valleys. Next up, picket wire, dinosaur footprints. I read about this, we were researching our vacation. And turns out that the picket wire dinosaur footprints, this is the largest track, the longest trackway in North America. And people don't know about this. But also the dinosaur itself is a four-legged sauropod, and they're very deep. So the dinosaurs were walking these long trackways, and it's preserved in Jurassic Age rock. And picket wire. It's a little bit south of Pueblo. We call it the Picket Wire Canyon. A lot of prints, 1,300, 100 separate trackways. About 150 million years old. We see dinosaur prints from Apatosaurus, Allosaurus, Camarasaurus, Diplodocus. We're actually going to see some Apatosaurus bones in a moment because we're going to go from here, from the trackway, to the National Monument in Colorado. Picket wire is not the original name of the area. Actually, it gets its name from the Purgatory River, but the early settlers couldn't understand the French missionaries' pronunciation of purgatory. They thought they were saying picket wire. So it's called the place Picket Wire. That's what it's a place name. Picket wire named after the farmers who thought the Purgatory River was picket wire. Still called picket wire, kind of funny. But just to give you an idea where it is. Here's La Junta, Pueblo is up that way, so this is kind of remote. To get in here, you have to register. They advise you to get if they require you to have some kind of four-wheel drive vehicle. So we got a big truck. Had to go to Colorado Springs to rent the truck. And we take off on this convoy, following these trucks, all the other vehicles. It's amazing what you can see here. Petroglyphs, sandstone arches. There's a fair amount of this human history, agricultural farms, or maybe a little town that was in there, mission, cemeteries. It's all in this area. Nobody lives there anymore. It's national grasslands. But the dinosaur footprints are in this area. We're approaching the fossil site, a little bit of an interpretation of the animals themselves. I think this might be an Apatosaurus. To get to the trackway, there's no bridge, no road. We just get together in a group and we cross the river. There's somebody monitoring so you don't slip. Pretty shallow. This particular kind of shallow water. There's a lot of fun to do that. The trackway itself is over here, so you have to cross the river. We get there and look at these amazing trackways. One last thing I want to say before I go to the next stop. The river that is exposing the beautiful prints is also destroying them. It's kind of a lesson in geology. I mean, the forces that, water forces that make this visible to us, the erosion of a landscape that makes the prints visible, makes the rocks visible, eventually destroy the rocks. And unfortunately, there's really no active conservation methods in place to save these prints. So over time, those erode away. It would take probably millions of dollars to put into some kind of stream diversion, remediation to save them. But right now, this is not even a national monument, it's just national grass. But these are the longest track. Moving on to the Dinosaur National Monument in Colorado. Now we're heading up north to the northwest corner of Colorado, north of Denver, northwest of Denver, not quite in Utah. The park itself kind of bridges Utah and Colorado. It's an incredible place, not just for the dinosaur bones that you see. The geology is just incredible. In fact, here's something right here. You can get in your truck and drive down to this river. And the site is fantastic. There are petroglyphs. It's just an amazing place to go. I'm going to focus mainly on bone stuff. Here we are in the hand diagram. shows you. Dinosaur ridge, dinosaur track, the Dakota. The Dakota hogback is right here. The dinosaur ridge is sticking out. You are in the Dakota group. This is the Morrison Formation. The Morrison Formation is the world famous formation for local dinosaur bones. It was discovered by a Florida guy who discovered some bones there, and he started to make quarry the rock, send the rocks back to a museum in Pittsburgh, 1909. He found some failed bones, kept working at it. We found complete skeletons. Sent them back to museums. People would come out to visit. By 1915, this was considered a national monument to protect it. It's hugely valuable. It's fantastic. We're going to see in these bones, there's millions, seemingly millions of bones in the rock. 100 million year old Apatosaurus. The location of the site is right here. Here's Utah, there's Colorado. It's pretty remote. Denver's down here. It's kind of a long drive. Not many people up there. Great place to vacation. You get there and the facility is world class. It is built into the side of a rock. So you're walking across the rock face, looking down at the dinosaur fossils. So you're in the building, you're walking along a walkway up here, you're looking at a wall of rock that contains innumerable dinosaur bones. In fact, there's so many bones, it's almost seemingly impossible to classify them all. They did reconstructions of that. So you can kind of figure out what you're looking at and the environment in which these animals are living. Presumably, it was kind of a trap for animals. They got caught in a landslide or something. And so you've got hundreds, maybe thousands of individual animals trapped. And then what we end up with are these bones that are exposed within the facility along this wall, which you can walk up to, get really close. They won't let you touch them inside the facility, but you can get pretty close. They're big. That's about 6 feet there. So these things are big. Lots and lots of bones inside the facility. And then what's more, you can go outside and walk along a trail that cuts across the Morrison Formation, so you can get back into older rock or up to younger rock, and you can literally see. I don't have anything. You can literally see a dinosaur bone sticking out of rock. I mean, it's not legal, but a person could just grab it and take it off. They're not supposed to do that, but it wouldn't be hard.
You said Morrison Formation is desert sandstone.
It was an arid fluvial environment where these animals were living and then got trapped. It's a floodplain, perhaps. There might have been a flood event, because the floods are very severe, intense in desert environments. And the interior of the continent at that time in the Jurassic period was very deserty, very arid. And there were big deserts in the Jurassic North America. That's where they were living there, evidently they had food to eat. Well, they might have been eating, other dinosaurs. But there were apatosaurs there in that rock, which were interesting. Yeah, here's the slide I was talking about. So you can walk a trail along the edge of the rock itself and look at fossils in place, in situ, literally protruding out of rock. It's quite an astonishing experience. I don't know if Ruth wants to see this or not. She should.
I know she did go to Yosemite and she did go to Arabian Rock. I don't ask her about dinosaur monument.
I don't think Dick has ever taken them. Well, I will encourage her. Okay, last stop before home is the Denver Red Rocks. This is near Denver. It's a world-class performing arts venue. It's in the suburbs of Denver. So here's the parking lot. You're driving. Here's the amphitheater itself. This is what it looks like at night. Remember that we're still in we're in the fountain formation actually, but still it's those highly tilted rocks of the remnant Rocky Mountains. You see, we're looking at the remnant of the Rockies. This is the remnant of the ancestral Rockies, situated in the modern day. So Red Rock Amphitheater is down here in, I think it's Jura. This is about 300 million years. That's actually Pennsylvania. And here's some of the events coming up. I just did a quick screenshot of what's happening. I'm gonna go to a concert. Got a ticket. And then we ended up, this is Frisco, Colorado, where my brother. Mainly it's a ski resort this time of year, it's just packed with skiers. But you go in the off season. The traffic is tolerable. You walk around, skiers paradise. We are somewhere here on the core rock of the Rocky Mountains, core rock. This is the Precambrian core of the ancestral Rockies. Frisco is right down here. The city is on rock of an age of about 1.6 to 1.7, so that pretty much matches the core rock of the ancestral Rockies. So you're living, Frisco is situated in the ancestral Rockies, about an hour's drive west of Denver.
So the Frisco rocks, is to say there that it's nice and like, so that's a lot of metamorphic rocks.
Yeah, it would be this core rock here, which is metamorphic mostly. There might be some igneous intrusions, still pretty old. Pikes Peak is an igneous formation. It's a little bit further south of Denver. Pike Peak is at this stage, but it's in the core rock of the Rocky Mountain. This is the core actually of the ancestral.
And the ones in the Dakota Hogback and the Fountain Formation, are those all sedimentary, or is it also metamorphic and sedimentary? And
They're mostly sedimentary, the Paleozoic age, because they were being deposited on this thing about 70 million years ago. So it's very, very ancient rock, but it is the core of the rock. Rocks. Let's check and see if so that concludes my journey. Thank you for your patience. Does anyone have any questions here? Good question.
On that, I had a similar, I geology student, I did my university. We did this very similar transverse rocks, and then the bad ones, ended up down Eureka,
Oh, that's where your camp was.
I, being from the east, I see gold and everything, and there's not a lot of holes, it's more.
Basin and range, I think.
Yeah, and so they that is upset.
You see how geology.
Yeah,
All thing.
yeah, we're always.
Yeah, the IU Field School is pretty intense place. We were there with students from Harvard and Yale, University of Chicago. They all wanted to go. So it all makes.
So does MA mean million ago?
Millions of years, MA, million. It's actually Latin for million annum.
Okay, it's Latin, okay. I get stuck on that.
It's just simply millions of years, yeah.
Yeah, I mean, I understood what it meant, but I couldn't think of the abbreviation, but okay, it's the Latin. I spent a year in New Mexico down, was camping on the southern slope of the ski slope, which I was told was the southern tip of the Rocky Mountains, but you're saying that the Rocky Mountains actually are in North America and South America.
They continue all the way through the Central America, the Isthmus, but into South America. It's a
So-
system.
So why did they call that the southern tip? I can't hear you.
Southern tip of the Rockies.
Yeah.
Yeah,
Well, there was another field trip I took, but I didn't explain it. That was to the Sangre de Cristo Mountains of New
okay,
Mexico.
yeah,
You see them, and maybe you know more about this
Yeah.
too. Sangre de Cristos are beautiful. They're volcanic. There's volcanoes, remnants all over the place. Beautiful rocks. That is in southern Colorado into New Mexico.
Mhm.
And they're younger because it's volcanic and, but they're all extinct volcanoes, but they're younger rocks. They're not maybe associated with the Laramides. Again, this is all kind of new to me. I didn't study up on the Sangre de Cristo. It was part of one of my trips. I just didn't talk about it today. But that would be the Southern Rockies. That would be the Southern Rockies,
yeah,
and that would be regarded as the tip, the southern tip of the North American Rockies, I guess.
okay, southern tip of the North American rock,
Right.
okay,
Yeah.
that makes sense.
Yeah, the point, but the book, when I read these books, the emphasis is on systems of mountains, not one continuous, because you have many things going on. You got antler mount formation over here, you've got some, what's that?
They're all sort of slightly different ages. Well,
No, it didn't come together all at once, and then the
Yeah.
continents were twisting too, there was, the whole continent kind of moved counterclockwise a little bit.
they kind of separate. Rock groups by age, by specific features of rock. So then, in the rock. You have different names. Like the other mountains, big ones.
Right.
Sandy dunes,
These are sub-events within a major. event. But I couldn't, I had to simplify this.
No,
Took me a
it's
couple of
fine.
weeks to
It's-
simplify this. Kept reading and reading all this stuff and just editing out what I thought was.
I like being where I was. In the southern tip of the Rockies, but this is a whole new thing happening in the South America.
Do we have any participants online?
Yeah, we have four. I don't, yeah, if anyone has any questions from Zoom, you can put them in chat, or you can put them in Q and A.
So you decided both of us?
Yeah. And then I would have
Any
a,
questions?
uh,
Open question.
some history.
Oh, Rick McGee's there. Rick McGee used to be the vice president of this club when he first started coming here.
Anyone here have any more questions?
I was curious what the temperatures were, like where you warm, cold, how was that variance?
Yeah, you gotta pay attention to that if you're traveling. Winter Bryce in the capital region, we would wear a jacket. It's high elevation, so you're kind of chilly. It'll warm up, so you can take your jacket off. But we would start the day with the jacket, better than Bryce. And this is probably, early June, or middle June. For the vacation to, spend some money, that was, I think, what, in July. And it's 100 degrees. It's a very dry. But it's 100 degrees heat. That's-
July and August, you mid that. The highest one in the day, and it was not for it, like. It was huge.
Yeah, in air, so it's very hot, but it's, will be good.
Well, where I was in New Mexico, it was 15 snow, right through, right into Maine,
At my elevation, you'll get snow in July.
right? Snow in July and at Mount Washington too. Yeah, I remember that was, I mean, it was really interesting, because you just go up, it was a fairly small drop up to this mountain, and you could see a lot of different, you could see these really alpine flowers. I.
Yeah.
15-minute drive from where it was about like here, and then the bottom of the mountain, it was, hot.
Yeah.
90 degrees.
Yep.
Well, if there are no more questions, I am going to stop recording.
You hear my name.